Dear colleagues, I'm glad to be with you at this conference. My name is Alexander Ledkov. I work at the Theoretical Mechanics Department of Samara University, and I want to tell you about the research that was conducted at our department under the guidance of Professor Vladimir Aslanov. Today I will talk about the problem of space debris mitigation. As you probably know, space debris removal is one of the most important challenges of modern astronautics. In 1978, Donald Kessler described a dramatic scenario of exponential increase of space debris caused by mutual collisions of orbital objects. As a result of pollution of low orbit, the launch of new spacecraft may become impossible. Currently, a huge number of space debris objects are in orbit. At the beginning of our century, two events significantly increased the space debris population. Destruction of the Chinese satellite in 2007 and collision of two satellites in 2008. Currently, more than 5,000 large space debris objects are located in orbit and pose a great potential danger. Various methods of space debris removal by an active spacecraft are discussed in the scientific literature. Part of the projects involves docking or hard capture of space debris by a manipulator and subsequent transportation by spacecraft's propulsion system as a single rigid body. Other projects propose to capture space debris by a harpoon, a net or other device and tow it on a tether. The third group involves contactless transmission of force impact on a passive space debris object. Contactless influence can be carried out by electrostatic, gravitational or magnetic exposure, by blowing the body with a high-velocity particle stream, or due to the evaporation of particles from the surface of the debris by a laser. Contactless schemes are more safe because they don't imply mechanical contact with space debris, and some of them allow to transport rapidly rotating objects. In our work, we consider transportation of object by high-velocity ion stream. The space debris transportation idea was independently proposed by two groups of scientists. According to the proposed scheme, a spacecraft flies up to the space debris object at a distance of about 10 meters. In addition to the main engines, the spacecraft is equipped with two oppositely directed electrodynamic engines. One of these engines is directed to the space debris object. It creates thrust P. To compensate it, an oppositely directed engine is switched on. The ion flow blows the object, thus generating ion beam force F like aerodynamics forces. This force provides the required transportation of the space debris object. The magnitude and the direction of this force depends on the orientation of the object in the stream, and a torque that seeks to rotate the object along the stream will arise. In this regards, it's very important to take into account the attitude motion of space debris objects in flow when we talk about a space debris removal mission. The work is aimed to study the space debris attitude dynamics during its ion beam transportation. Before we go any further, let's introduce a few assumptions. The planar motion of the system will be considered. It's assumed that space debris has a cylindrical shape. The spacecraft control system is capable of maintaining a constant distance to space debris. And finally, only gravitational and ion beam force and torques act on the object. Lagrange equations of the second kind are used to develop a mathematical model. The considered mechanical system consists of a material point A and a rigid body B. Non-potential forces and torque act on the system. Force P is total thrust force of the spacecraft. F is the ion beam force and Lz is ion beam torque. The state of the system can be determined by 5 generalized coordinates. corresponding generalized forces can be calculated using expression 2. Lagrange function of the mechanical system is shown on the slide. This function includes the kinetic energy of the spacecraft, the kinetic energy of the space debris, the potential energy of the spacecraft as a material point, and the potential energy of the space debris object as a rigid body in a central gravitational field of the Earth. Substituting the Lagrange function and generalized forces into the Lagrange equations and expressing the second derivatives gives the following system of equations. The system is rather cumbersome. Let's simplify it. If the relative coordinates of the spacecraft are held by its control system and the radius of the orbit is large, then the equations of motion can be reduced to 3 equations. Since the magnitude of the ion beam force is small, we assume that the center of mass of space debris moves in a Kepler orbit. We pass from time to new independent variable, which is the true anomaly angle. In this case, the equation of attitude motion of the passive space object takes the form 8. In the case of small eccentricity, we expand the equation in the Keplerian series and discard nonlinear terms. We represent the ion beam torque in the form of a series and finally obtain the equations of space debris rotation in an elliptical orbit of small eccentricity. In the case of circular orbits, the equation is simplified. Let's introduce a parameter gamma that determines the ratio of ion beam and gravity gradient torques. We use this simplified equation to analyze the space debris motion. As an example, we considered the orbital motion of a cylindrical space debris close in shape and mass to Ariane 4 H10 stage. All parameters are given on slide. We consider 3 cases. In the first one, the center of mass of the cylinder is in the geometric center. In the second and third cases, center of mass is shifted to the upper edge. To calculate the ion beam torque, the methodology described in the papers 3 and 4 was used. The cylinder was divided into small triangles and the force effect on each of them was calculated. The graph shows the dependence of the ion beam torque on the angle of object's deviation for considered cases. For each of the cases, a series of calculations was performed for various gamma parameters using the unperturbed equation. As a result, bifurcation diagrams were constructed. The diagram illustrates the location and type of equilibrium positions of an unperturbed system. The bifurcation values of the gamma parameter can be seen in the diagram. A bifurcation point, this is a point at which the equilibrium position appear or disappear. Let us consider third case in more detail. We take a few gamma values on the bifurcation diagram. For each value, a corresponding phase portrait can be constructed. Black lines correspond to unstable saddle points and blue lines correspond to stable center type equilibrium positions. The bifurcation diagram shows how the phase portrait deforms when the gamma parameter changes. According to the bifurcation diagram, 2 bifurcations are observed. When moving toward an increase in the gamma parameter, at first 2 equilibrium positions disappear, which corresponds the transition from the phase portrait shown in the gamma 3 section to the first portrait of the gamma 2 section. Then 4 new equilibrium positions arise. With a decrease in the orbit altitude, the gamma increases. Therefore, a situation is quite possible where during the descent from the orbit, the phase trajectory will fall into new oscillation regions, as a result of phase portrait deformation. Since the phase portrait of the unperturbed system contains unstable saddle points and the perturbation is periodic, we can expect the presence of chaos in the system. Poincare sections are an effective tool for analyzing chaos. Chaotic regions are visible on the sections as a cloud of points, while the regular trajectories form curved lines. The presented graphs clearly show the chaotic layers around the separatrices. The thickness of this layer increases with an increase in eccentricity of the orbit. Another tool for analyzing chaotic motion is Lyapunov spectrum. The spectrum for the trajectory starting at the red dot is shown on the slide. It contains a positive, 0 and negative value. Such set indicates that the trajectory is a chaotic trajectory. Thus, a simplified mathematical model was constructed and a study of a space debris object motion on an elliptical trajectory under the influence of the ion beam was made. It was shown that with a decrease in the orbit altitude, deformation of the oscillation region occurs. In addition, chaotic area of motion exists. This phenomenon can cause a sharp change in the space debris oscillation's amplitude during its contactless transportation, and these features should be taken into account when developing space debris removal mission. Well, that's all I have to say. Thank you for listening. I'll be happy to answer your questions in comments. Thank you.